with you. So your quizzes from last time were coming around. I'm sorry, I'm actually grading the retakes, and I haven't graded the retakes yet. So I will get those graded by next Tuesday, I promise. But those are the actual last quizzes you took, and yeah, you can go ahead and start circulating them. All right, so I'm actually quite excited because I've been thinking about what we're going to be doing for the next couple of weeks, and quite honestly, this is probably in some ways, my favorite part of the course, and it's one of the main reasons why I restructured the course this semester compared to how I've taught in the past, because it used to be I didn't get to this material to the very end of the semester, and I wasn't even guaranteed to get through it all. So the stuff we're going to be doing over the next couple of weeks leading up to spring break, to me, is actually some of the most interesting stuff that we're going to do all semester, and it's where all of the sort of work and formalism that we've been wading through is really going to pay off. Okay? So things are going to get fun reasonably quickly, but before they get fun, we have to go ahead and finish our story about Lagrangians and actions in particular. And so what I'm going to do right now is I'm just going to very, very quickly do a lightning review. By the way, who did the reading? Okay, so here we go. From now on, lecture is going to start with me drawing a card and having that person tell me what we're covering that day. You have to do the reading. And the reason you have to do the reading is as follows, and I think I explained this to you before. It is a well-researched idea in active learning that just getting your brain going at all, even if there's not detail, just saying, oh, that's what we're learning today, makes you benefit from the actual content of the lecture more than if you just come in completely blind going, I have no idea what the hell we're talking about today. Let's see what Florida has got. Okay, just having an idea of what's going on is going to give you more benefit from the lecture. Just thank me that I'm not assigning you chapters from a book to read, because I know that will never happen. Right, so I'm taking the time to write these things, so take the time to read them. I don't care if you read them right before you come into class. They're a paragraph, for God's sake. But I'm going to start every lecture by drawing a name and asking that person to tell me what we're going to talk about today. Okay? So with that in mind, what we're going to talk about today are actions. And so I'm going to go very quickly through just a simple example. So for many of you, this is something you would have seen before. So I'm going to do a two-dimensional example of an action where the functional is a function of two unknown position functions, x of t and y of t. And of course, we can think of this as the vector position, and we will eventually adopt a vector notation. But I'm going to take this to run from t1 to t2, and I'm going to have L some Lagrangian that depends on x, y, x dot, and y dot, and we're not going to have to concern ourselves with explicit time dependence on the Lagrangian for the purposes of this course. So if you want to think about those subtleties, you can consult your intermediate mechanics book. So as we talked about last time, well, if I adopt a vector notation, then I'm going to refer to this as x vector of t, and then of course the Lagrangian is just going to become the Lagrangian of x and x vector dot. Okay, so I'll actually work with the vector notation, but just keep in mind there's two undetermined functions. And then what we want to do in order to apply the action principle, remember the action principle says that I take this action functional. Alexander, where are you? Is Alexander? Oh yeah, remind me what a functional is? Say it again? Something that functions. Junction, what's your function? You know phrase. I'm sorry, you guys don't know that song, obviously. So it functions, but what does it do? What do you put into a functional and what do you get out?
You put in a value for, in this case, the x of t, and what you get out is what the s acts on.
Anybody want to help them out? Jacob?
So you put in a function and then get out a number.
Yeah, you put in a function and get out a number. That's different than a function because for a function you put in a value of the argument, so you put in a value of x and you get a number out of the function. So you feed functionals functions. So when you said it functions, that was a little like See, right? Because you're right. Okay, anyway, all right. So if we put in various functions for x and y, and then of course include their time derivatives, and then we integrate all that with respect to time between two specific limits, then that's going to give us a number. And the idea of the action principle is to vary this thing and demand that its variation with respect to all degrees of freedom vanish. Okay, so we're going to work this out explicitly. Okay, so what we're going to do is we're going to work to first order. So let's consider, and everything I'm saying should be in a way of review if you've taken Physics 350. So this is not what I want to teach you today. I'm just reviewing this so that you have some context for the real topic that we're going to get to. If I take a trajectory and I consider, how do I want to do this? I want to label this. I'll label it this way. So if I take a trajectory and I consider a small perturbation around the trajectory, where the perturbations at the endpoints of the integral are defined to vanish. Okay, then what I have in mind is I start at some initial and final position, and there's some true path. That's the classical path of motion that this particle, for example, if that's what you're describing, would take. And this would be described by x of t. And what I want to do now is I want to consider a small alternative path, okay, that is deformed away from this by this small value delta x of t, subject to the constraint that it has to begin and end at the same point. So the variation has to vanish at the ends, okay? Because I want my boundary conditions to apply to all possible paths that I'm looking at. Okay, so this is sort of a picture of what we're doing. Then what I can do is I can expand the action to first order in these small variations, and if I do that, I'm going to get something that looks like the following. So I can take the partial derivative of the Lagrangian with respect to the path itself, and then dot that with the variation of the path. So think of this like a Taylor expansion. Okay, it's the first order term. It's the first non-trivial term. So this is computing delta s. So s would be, the new s would be s plus delta s. Everybody follow? And I'm only focusing on the change in the action, because this is the thing I want to vanish. Okay, so when you Taylor expand, your first terms, okay, are your deviation away from the constant value. Okay. So we're just looking at these first order terms because we're computing delta s. Okay. And then of course I could have a contribution that comes from the changing time derivative. Okay. Now, what I want to do is eventually say something like delta s over delta x bar equals 0. And looking at this, that almost kind of makes sense, because if I just took this guy and shoved him under here, then that would be a delta s delta x bar. But the problem is I can't really do that with that term because it's not delta x. Yeah?
You have partial L, partial delta x dot.
Yeah, sorry, that should be x dot. Sorry. I really need to look at my notes before I write something on the board instead of going all maverick on your asses. But anyway, okay. So what we're going to have to do is we're going to have to massage this term a bit. You guys ever heard of massaging? I lived in Australia for a while, so it's always massage instead of massage. But anyway, we're going to massage this term, and we're going to get it into a form where we can actually just extract a delta x instead of a delta x dot. Okay, so the way that we're going to do that is we're going to consider the total time derivative of delta x dot partial L partial x dot. Okay, if I take the derivative of that just using the product rule, I have so the variation commutes with time derivative, so this actually just gives me delta x dot. But then I pick up a term from the time derivative acting on this guy. Okay? And you already see kind of parts of the story that might be familiar to you. This looks like a part of the Euler-Lagrange equation of motion. And what's nice about it is it's multiplied by delta x, not delta x dot. And what we're trying to get is the overall delta x that we can pull out. Okay? So then the question is, what about this term? Okay, so the story that I'm going to play is, of course, integration by parts, right? If I'm integrating this thing, well, this is this, so I can replace this with this minus this. But then I'm integrating a total time derivative. If I integrate a total time derivative over a time interval, that's just the integrand evaluated at the endpoints, and then the integral of what I'm left with. Okay, so that's just a integration by parts. All right, nothing fancy there. But what's the wonderful thing that happens to this?
Goes away
Why?
because the variation vanishes at the
Right, the condition on the variations is that at the endpoints they vanish, because we want to consider paths that begin and end at the same point in space. So it's this contribution that's vanishing. By virtue of that, this is 0, and so at the end of the day, my action can be written as T1, T2, delta x, dotted with partial L, partial x, minus the derivative with respect to time of partial L, partial x dot, all integrated with respect to time. But now we make the claim that if we want this variation to vanish for an arbitrary path, as long as that path meets the boundary conditions, then this quantity need not vanish. It's arbitrary. The only way that this is going to vanish is if this quantity itself vanishes. All right? And that, most of you readily identify as the Euler-Lagrange equation of motion. Okay, so there it is, derived from an action principle. So let's write that down. So in this context, minimizing this thing leads to partial L, partial x vector minus the derivative with respect to time of partial L, partial x dot equals 0, where you should bear in mind that this is actually a set of equations, one for each direction. Right? That's what this vector notation means. All right? Now what do we do with these?
You do it.
solve them.
You solve them! Yeah! They're differential equations. They're your best friends. Okay? No, they're your worst enemies. You're solving for these unknown functions x of t and y of t. Of course, you have to apply the boundary conditions. Okay? But if you find for a particular set of boundary conditions solutions to these differential equations, those are the paths that minimize this functional. So you could literally find the x and y of t that satisfy these equations with a set of boundary conditions, plug them into this integral and get a number out of it, and then if you pick any other x of t and y of t, arbitrary, that satisfies the same boundary conditions and plug it in, you'll get a larger number, or maybe a smaller number. Why do I say that? Because this is an extremization procedure. It's not necessarily minimizing or maximizing. I can't take you seriously when you're doing that. Okay? But at any point, if you put in enough functions, you'll realize the contour of the space of values that you're getting out of the action function, and you realize, oh, that's a maximum or that's a minimum. We don't actually do that. We just solve these equations and say, that's the answer. Yes?
If you wanted to guarantee that it was a minima, would you have to go to second order in your approximation for the variation?
If you wanted to guarantee that it was a minimum,
Yeah.
you mean check that it's a minimum or force it to be a minimum?
Force it to be a minimum. Like get a second set of equations?
Get a second set of equations?
Yeah, by taking the variation of S to second order so that you pop out some second order derivatives.
Yeah, if you looked at what's happening in the second order, that would tell you whether it's a maximum or minimum. Yeah. But you can't force it to be a maximization or minimization problem. That's actually dependent more on the Lagrangian that you're picking. It actually has more to do with the metric of the space. And this is the reason why we have to use just extremization in general, because in real space, without time, without a negative part of the metric, the action tends to be a minimum, or the equations of motion correspond to a minimum of the action functional, but in special relativity, it's actually a maximum of the functional. But we're not going to concern ourselves. All we need to do is extremize it. Okay? Okay, so what can we do with this? Well, if you took 350, you know you can do a lot of really painful stuff with it. And I'm not really interested in doing that so much. But let me sketch for you a couple of the ways that we can use this. And then what I'm going to do is generalize this procedure to relativistic field theory. So by the way, what we just did was non-relativistic point particle. Okay, that's the example that we just did. And the reason I know that is because we integrated something with respect to t. Okay? In relativity, you would never do that, because t is not special. The reason I know it was a point particle is because my degree of freedom was given by that. And for point particles, this is what we use for degrees of freedom. Where is the point particle as a function of time? We're going to generalize that procedure to a relativistic setting for fields, because that's what we're interested in this class. Okay? But before I get there, let me show you a couple of ways that we can make use of these actions. So we already know that classically, if we get the Euler-Lagrange equations and we solve them, then that gives us the classical behavior of the system, the unique classical behavior of the system. Unique because classical physics is deterministic. Okay? You're future tellers in classical physics, right? You give me the boundary conditions, you give me the equations of motion that govern things, and I can tell you what's going to happen. All right? And I don't even have to wear a weird headscarf and have a big ruby ring on or anything. Or take money, although I will take money. Secretly, I'm taking your money. Let's just not think about it that way. Because then I work for you, and that's not the way it goes. Anyway, so, but I argued to you that the Lagrangian formulation and action principles are actually much more useful than the limited context of classical physics. We're going to see how you can generalize it to relativistic fields, but the Lagrangian formulation and actions also serve us in quantum systems. Okay, so in a quantum mechanical context, what we do, and we're not going to go into a lot of detail with this, but I just want to give you a sketch of what it looks like. We take the action for a system, so let's just concentrate on a non-relativistic point particle, but instead of varying this and setting the variation to 0 to get the Euler-Lagrange equations, which we solve for the classical motion, we do something different. What we do is we pick a path, any path you want that satisfies the boundary conditions, and for that path we evaluate this quantity e to the I s over h bar, where s is the action evaluated with that path. Remember, you stick a function into the functional, you get a number out. Okay? So this is just a number, and I get a different number for each and every path. So if I have these two as my boundary points, I can pick this path, and I can pick a different path. And every one of these paths, I stuff into the action, and I get a value for s, and for that path, I construct this factor. Okay? Then what we do is we add all of these together. So if I label my paths by k, then I can sum over k. And if I do that, then this quantity, and I think that might actually be squared, and I left it out of my notes, but this quantity is the probability. I'm going to write squared here because I'm pretty sure it's squared, but is the probability for the particle in question to move, for this to actually happen, from x at t1 to x at t2. Okay? Now we know in quantum mechanics we're never going to predict what's going to happen. That's not the way quantum mechanics works. The best thing you do is you calculate probabilities of things happening. So here, the process I want to calculate the probability for is if the particle starts here, what's the probability that it goes there? Okay? And it turns out that to evaluate that using these tools, I consider every possible path, construct this little quantity, and add them together. Well, there's a natural name for that procedure. Anybody know what it is? It's a path integral. Okay? So this is the path integral formulation of quantum mechanics. All right? It's very much inspired by getting an interference pattern from a double slit, sending a wave through it, and asking, how in God's name do you get that if these are particles, right? Well, wave-particle duality says that you don't have to think of them as particles, you think of them as waves. And we know if we send a wave into a two-slit apparatus, we get an interference pattern, but the way that we get that interference pattern is by considering both of these paths to get to any given point. And there's a phase difference, and that corresponds to the interference pattern. But you have to sum over both paths, going through both holes. Okay? This is just a continuum analog of that, because there's a continuous number of paths.
Oh, I think you just, were you saying that you could integrate over the path?
Yeah. So here I put a discrete index, k.
Yeah.
And in a situation like this, it would be discrete. There's two ways to get to the screen at any given point. You can go through this hole or this hole, so you'd sum. But this is a continuum of paths. And generally, there's going to be a continuum. So this would actually be an integral over paths.
Over paths. So in this context, for the double slit, you'd integrate over the outgoing paths?
So you take this point and you take this point, and you sum over those two paths. You evaluate the action for each of them. Make e to the I s over h bar for each of them. Add them together. Take the square of the magnitude, and that's the probability for the particle to go there.
Do we not need to worry about like odd paths that we go through, or do they only have to be straight lines since it's light?
Do we have to worry
If
about?
you're saying there's two paths, is there not some probability that would kind of?
You're talking about here?
Yeah. Or is it
He's
not?
saying, do they have to be straight lines?
Have you guys not studied double slit interference?
Well, yeah,
We
what
did
I'm saying
bond
is because
physics.
it's
Okay, so there's no interaction here. So a particle or a wave would just travel in a straight line.
Okay. So that's what.
So the only thing that can happen is when it passes through the opening, it can diffract, it can bend. So there's no, in this context, there's no point to entertain the notion of a path like that. Here I'm just saying, I don't know what the hell's going on, but I have to integrate over all possible paths. Okay?
So we're talking about it a little bit more in a deterministic way than.
Yeah.
Than just saying there's 2 points that can be.
Yeah, I don't want to get hung up on this because we're not going to actually work through the mechanics of it. We're going to use the results of path integrals to evaluate Feynman diagrams in the second part of the semester. But all I'm trying to do is motivate that basing everything on Lagrangians and actions is useful both classically where you're familiar with it, but also quantum mechanically. And we're going to evaluate this path integral. Okay, not from first principles, because this isn't a quantum field theory course, but I'm just going to show you how to evaluate it using these famous Feynman diagrams. So you'll get some more insight in due time. But you can read about path integrals in any, hopefully in any quantum mechanics textbook, because it's not special to particle physics. It's not even special to relativistic field theory. You could do non-relativistic particle physics with it. Okay. All right, so if we want to relativize everything, yeah, if we, hold on, no, I have one more comment. Yeah, so one more comment. And again, this is I don't want to get hung up on this, but I feel like this is a relatively important comment to make. So to go from quantum to classical, what is the usual statement that we make? If you want to take your quantum system to be classical, you can just take the limit that
Big numbers, big.
right, it turns out there's many different ways to say it. I mean, perhaps the most common is to say take h bar to 0. Okay? Well, let's ask ourselves, does that somehow give us, in this path integral thing, a connection to classical physics? And the answer is actually yes, because what happens is the weight, we call this the weight factor for each path, you'll notice that as h bar goes to 0, this thing starts oscillating like a mother. All right? It's e to the I of a very large number. Well, it's e to the I of a very large number if s is bigger than h bar. So technically, it's not so important that h bar go to 0, but that the action of the system in mind is much, much larger than h bar. And then what happens is if you look at the space of I guess we can say actions, and I'm going to be very hand-wavy here, but I just want to give you the idea. If I look at the space of possible values of the action, evaluated over different paths, what I find is that around for example, a minimum, paths here and paths here, when they're rapidly oscillating, cancel each other out. Okay? So when you do this sum, contributions from neighboring points around a minimum or a maximum effectively cancel each other out in contributing to the probability. The only paths that count in this limit are the ones that don't have something to cancel them out. That's these. But that's exactly the classical behavior. Okay? So this is it's called the method of stationary phase, and that's what you want to go and read about if you want to understand the classical quantum correspondence limit in the path integral formalism. Okay? Yeah?
Are you sure that's a probability? I think it's just the time evolution operator.
The time evolution operator would be e to the I, the Hamiltonian, not the action. Right?
Hamiltonian times time, so it's essentially action.
I'm
fairly certain it's a basis change into like a Hamiltonian formulation, and then you change your basis back, and that's essentially integration. But I don't think we're referring to it as a probability.
if Marie is right, I will clarify it next time. I have a good feeling you're wrong, but I don't want to go into the details. I won't be able to flesh out the details of it right now, because I don't ever think about path integrals in a Hamiltonian context. Okay? But, yeah, we'll have to talk more about that later, and after I go and read a little bit more about how this looks in the Hamiltonian formalism.
You say that they cancel, implying that it's symmetric around the minimum. So is there any, how do we know that it's symmetric? Or we just assume it's symmetric around the minimum?
You're evaluating all, let me think. So, okay, this is a very, very heuristic picture that I'm drawing for you, okay? I want you to imagine instead that here I have a path, the true classical path, and for every deformation that I could consider a symmetrically opposing deformation, okay? Clearly, this is, plotting the action as a function of one axis, where I'm calling this axis all possible variations of the path. It's not an accurate picture. Okay, and then drawing some curve is not accurate either. Okay, so this is very heuristic. So, but you can always, for a given path and a given deformation, you could choose a symmetrically opposing deformation, and then the rapid oscillations between those two is what would cancel out. But yeah, I don't even know what curve you would draw that would be symmetric.
That's assuming that it's a minimum or a maximum, not a set point.
Right.
Actually,
Right. Okay, yes. So I now want to move on to what this looks like for relativistic fields. And I'm not going to go through the derivation of the Euler-Lagrange equations from an action principle because it looks almost identical to what we just did for the particle. So I'll just be writing a lot of stuff on the board that's not really that useful. Okay, so for non-relativistic point particles, we used integral of a Lagrangian with respect to time, and then the degree of freedom that we were working with was the position as a function of time. For relativistic fields, instead, our action is going to be a functional, not of this, because for fields, we don't say the field is here at a certain time. The field is defined everywhere. Okay? It's how the field varies over space and time that is of interest. Okay? So the functional will be a functional of the field, which itself is a function of space and time. Okay, and I'm just going to call my field phi for right now, and we can talk about different kinds of fields in due time, and we'll look at some examples today. Just as, well, actually, let's just go here. I can set this up as an integral of a Lagrangian, but we've got for the relativistic case and for the field case a different kind of Lagrangian that we have to use. First of all, we know we're not going to be integrating over dt because we're in relativity. Time and space should somehow be on the same footing. But also here, our paths only depended on t. The fields depend on x mu. So when we integrate the Lagrangian in this case, we should actually expect to be integrating over all four coordinates. Now d4x has a technical definition. It's actually the wedge product of infinitesimal differentials in each of the coordinates, and that creates a certain kind of transformation under coordinate transformations, which is canceled by the fact that this is a Lagrangian, this is not a Lagrangian. But that's a technical detail we won't worry about. The point is, when I write d4x, you can kind of think of it like dx, dy, dz, dt, but it's not. It's a little more complicated than that, but we're not actually going to be doing these integrals, so it doesn't matter. All right? This Lagrangian is now going to be a function of phi. Okay, we expect that. But remember that in the non-relativistic point particle case, our Lagrangian was often a function of position and velocity. So now we have to include, by analogy, the velocity of the field. I know, what the hell does that mean? Well, this is just telling you how the position is changing with time, right? Well, what I want to put in here is how the field is changing with position in space-time. Well, that's just d phi dx mu. It's just the derivative of phi with respect to x mu. So this is what you can think of as the velocity of a field. It's not really the velocity, it's just a gradient. Is the field changing at all? Okay. All right, now with that in mind, the Euler-Lagrange equations that you get by varying this with respect to the field and setting the variation to 0 at first order actually look exactly like what you might expect. So remember that in the non-relativistic case, our Lagrangian looked like this. You can literally take this thing and relativize it. So I'm going to call him Matt. Matt talks too much. David. If you were going to guess what the relativistic version of that looks like, what would you say? Just guess.
Partial of R Lagrangian.
Partial what?
Partial of R Lagrangian over.
It's the Lagrangian density, technically. We'll just call it the Lagrangian. But the script L is to remind ourselves it's actually a field theory Lagrangian, which has to be a Lagrangian density instead of Lagrangian. But anyway, it's technical. We'll just call it the Lagrangian.
With respect to x mu.
With respect to what?
X mu.
So what is this term? It is the derivative of the Lagrangian with respect to the degree of freedom.
So the field.
Yeah, 5. Good.
Minus the derivative of 4. Because we're not going to use t.
Right, so what do you think we would use?
X mu.
Yeah, so d by dx mu of
R Lagrangian density. Or the script L.
I can't tell what you're saying. Yeah.
The derivative of the script L over our field velocity.
The field velocity, which is this,
Yeah.
okay? So remember, I think I said this earlier, we're going to write this as d mu phi. It's just a shorthand, because this d by dx crap gets old really fast. So I'll call this d mu phi. Okay? You could have calculated it, but you could also just guess it. All right, does anyone have any issue with connecting these two? You kind of see why I put things where I put them and what I chose? Yeah.
Is there a Lagrangian for like a low dimensional?
Yeah, it looks the same. They look exactly the same. I mean, you'd make that D11, but the Lagrangian, Euler-Lagrange equation of motion are the same. Yeah.
How many have that?
Yeah, we can't. I got too much to get through to entertain like fun questions, you guys. So you got to ask clarifying questions. You should come to office hours and ask these questions. I'm telling you. Yeah.
The derivative that we're defining there up in the top right, is that at all related to the linear one we discussed?
Yeah, we'll talk a lot about that later. We're going to get to something very similar to that. But for right now, it's just a coordinate derivative. So if you guys are concerned about what this means, this has an index. It's actually a dual vector index, and what it means is you take the derivative with respect to ct, and then there's one where you take the derivative with respect to x, ... and those are the components of a dual vector. That's why this notation is better, because we can look at this and go, oh, mu is lower, therefore it's a dual vector. In this notation, it's like the mu is upper, but it's in the bottom. But it turns out that a mu upper in the bottom actually acts like an overall mu lower. So people prefer this notation. In fact, we should just quit jerking around and call this d mu. Okay? And the thing you'll notice is, and again, it's unfortunate, This is a mu that's lower in the bottom, which means that overall this mu is upper, which is good because it contracts with this to go away, which it needs to do because there ain't a damn mu here. This has no mu. This is a scalar. This should be a scalar. And these mu's actually are one up and one down, and they go away. They get summed over. Okay? Yeah.
So our relativistic Euler-Lagrange equation here, when we solve it, the quantities will still be invariant because the whole thing, it's all getting summed over.
So the equation of motion, so this is actually a very, very deep thing that we're going to talk about in a couple of weeks, and it's the question of whether the solutions have to be symmetric if the equations or the original Lagrangian is symmetric. And we're actually going to look at an explicit case where you have a symmetric Lagrangian, but the solution is not symmetric. And we'll sort of explore why, and you'll understand it better in that context. But I don't want to steal the thunder of that whole discussion, because that's a big part of the Higgs mechanism, which we'll talk about in a couple of weeks. Okay. So, look, there's certain rules that you can't violate, and that is you know that you just can't add a number plus a vector. Like, I don't care what amount of physics you've done, you never do that. Okay. And that's essentially what I'm pointing out here. This is a scalar, so this thing better be a scalar overall. If this were a vector, it would be fine if this were a vector, okay? But since this is clearly a scalar, there's no index, then this has to be a scalar. Now, all of this is predicated on the assumption that phi itself has no indices. And we'll look at cases where the field itself has an index in just a minute.
What do we solve for here, this equation?
What are we solving for if you... So if I give you boundary conditions and you solve this equation subject to those boundary conditions, what are you finding? You're finding the field and how it varies over space. So, you've got a field, and then you plot all of the space-time axes. And, this is going to be hard to draw because there's 4 of those. And then this is kind of like a surface, but it's not really a surface because it's living over 4 dimensions, right? You can't draw it. I mean, you can kind of think of in 3 dimensions, like if you were trying to find the density of the ocean, that would be a density field.
Okay.
So it would have values at every point within the ocean, and the value would be the density at that point. Okay. All right. So now I'm going to get a little meta on your asses, and then we'll look at some examples. So, okay, so when you've worked with Lagrangians in classical physics, you're used to the idea that the Lagrangian is often written as T minus V, where this is the kinetic energy of the degrees of freedom. Okay, that's one of the beautiful things about Lagrangian mechanics is you can restrict yourself to only the genuine degrees of freedom. So, if you have something riding on a roller coaster track, that's a 2-dimensional motion, but you can just parameterize everything in terms of position along the track and make it a 1-dimensional mechanical system. So the T is typically the kinetic energy associated with your degrees of freedom. And then the V corresponds to what? Mark. Say again? Yeah, this is the potential energy. Okay, everybody familiar with that? Now I'm going to write a more general form of a Lagrangian. You guys, what is so funny? Do I look weird? Have I got like a bugger hanging on my nose or something? Huh? All right, you guys are killing me. Okay, I'm going to write a different form of a Lagrangian, which is equivalent. I'm going to say that the Lagrangian, and I'll just go ahead and write with script L. It doesn't matter. You can say the same thing in a classical point particle case as you can in a relativistic case. The Lagrangian is a kinetic term okay, plus an interaction term. Now, you might say, wait, Flory, where's that minus sign? Well, I haven't actually told you how you build this, so the fact that I call this plus or minus means nothing. Okay? This minus is important because you have a prescription for how you build the potential energy, as well as a prescription for how you build the kinetic energy. But I haven't really said anything about this, so I'm just saying combine them. Yeah, maybe at the end of the day there'll be a minus in this and it'll look like you're subtracting it. Okay, but that's a detail. But generally speaking, when we do Lagrangian mechanics, we have degrees of freedom. And those degrees of freedom can be very different things. It can be the position of a point particle. It can be a field configuration. Okay? It can be other weird things. But those degrees of freedom, if they can change, if they can vary, then they need to have a kinetic term. There needs to be some part of the mechanics that allows them to vary. Otherwise, it's a very boring system, right? It can't do anything. So this is almost essential to have degrees of freedom when you're doing something interesting. This controls their behavior. This is what makes them do interesting things. Of course, if I take a particle and stick it in a Coulomb potential, that you can model with this, a potential energy, but that's an interaction. It's the interaction between the charged particle and whatever's creating the Coulomb potential, typically in a hydrogen atom, the proton. It's an interaction, okay? Now the reason I'm saying this to you is because there's a methodology that we're going to employ in the next couple of lectures. And that is we're going to start solely focusing on this term, and then we are going to, by a very beautiful procedure, generate that term, okay? But are there any questions about this split right now? Yeah.
So you mentioned interactions for example, with the Coulomb potential with the electron and center of the electron. But aren't we working with relativistic fields, not particles?
Sure. I mean, I'm not saying that we're going to have potentials. I'm just saying this is an interaction term. And the interaction, this is a very, very broad brushstroke right here. The word interaction can mean a particle interacting with a field. It can mean two fields interacting with each other. That's what we're going to see. It's the interaction of two fields with each other. So in that case, if you want to describe the motion of the electron in the presence of a hydrogen nucleus, then you would be describing the interaction of the electron field with the photon field. Two fields. Okay? But I'm just saying, this is things interacting with each other to create interesting changes. Okay? Everybody on board? All right, so if I set this term to 0, then what kind of theory do I have? Boring?
Kinetics.
I have a non-interacting theory, right?
Free particle.
Yeah, I have what's often called a free particle. So the kinetic term is often called, and we'll use whatever word we feel like at the moment, the free Lagrangian, because it's the only thing you have if you have a non-interacting system. Okay, so sometimes I'll say kinetic, sometimes I'll say free, but hopefully the context will make it clear. Okay, so what we're going to do now is consider how all of this plays out for the free Lagrangians that are actually relevant for the standard model. All right? So I'm sure I'll need this later, but I'm going to go ahead and write it. So in classical physics, if you just have a point particle that's moving, what's the free Lagrangian? Say it again?
1/2 mv squared.
Yeah, it's 1/2 mv squared. Okay? This has a lot of drawbacks if you want to try and relativize it, right? You know, this is v, we got to somehow make that a different kind of velocity, but more importantly, this doesn't make sense if things are massless. And we know that massless things exist in relativity. So you might guess that our free Lagrangian is going to look somewhat different than what you're used to. All right? It's still going to involve a generalization of velocity, because that's just things changing. And it's still going to depend on mass, because mass is important in relativity. It's just some things don't have it. Okay? So when I write down the free Lagrangians that we're going to be working with, you should expect them to look a little bit different than this. So this is a point particle. All right, so what we're going to do is we're going to go through these one at a time. And we're going to start with spin 0. See if I can. So for relativistic fields, I'm going to do the 3 cases. And we're going to start with spin 0. So spin 0 corresponds to what we often call scalars. And in the standard model, the importance of scalars is actually pretty small at the fundamental level. The only scalar in the standard model, fundamental scalar, is the Higgs boson. But of course, it's a part of the standard model, so we do have to know how to handle scalars. There are composite particles that act as scalars. So the pi meson is a combination of 2 quarks, but the spins are anti-aligned, and so overall it has spin 0. And if you want to just describe the behavior of the pi meson without worrying about its quark substructure, then you would treat that as a spin 0 particle, but it's not fundamental. The quarks are fundamental. Okay? The only fundamental scalar particle we have is the Higgs. All right, now the Lagrangian for a free scalar particle, or the kinetic term, if you will, looks like this. And again, it's going to look a little different than what you're used to. Okay? Now, let's see. Henry. Where's Henry? Yeah. Henry, looking at the non-relativistic point particle case, if you were going to try to identify this term with something, what would you identify it with? So something up here. We'll start with an easier question. If I were going to identify 1/2 with something, what would I identify it with?
Is it the velocity term?
Yeah, it's the velocity. So like I said, you should always expect something like a velocity term. Of course, it's not going to be velocity, it's going to be the derivative of the field. How is the field changing? Okay? Now, you might say, well, Alex, why don't you just multiply this by m and then you have an exact analogy? But this doesn't work for massless particles. And that's okay, because it's not right anyway. You actually have a separate mass term. I mean, there's m. This clearly plays the role of m. So this is a mass term. Now, you might say, well, why does the mass behave so differently? Well, remember, in relativity, mass already plays, even in non-field theoretic relativity, mass already plays a weird role, right? You have energy if you have mass, even if you're sitting dead still. Even if your V is 0, you still have a rest mass energy. And indeed, even if the field was perfectly constant, if the field is excited uniformly, so the derivatives vanish, it's uniform, but because it's non-zero, you have a contribution to the Lagrangian because it has a mass. So you can think of this like, if a particle exists, it has to have a minimum energy, the rest mass energy. Okay, even if the particle's sitting still. If it's moving, it gets more. Yes?
So why is it subtracted from the velocity?
Okay, so all right. So I'm going to do a lot of this today. And I'm going to try and do my very best to point out things that might be familiar and intuitive, but there are a lot of details that we are simply not going to be able to completely go through. So if you want to know where this Lagrangian comes from, let me first get the equation of motion, and then I'll explain to you, because most of the stories that I'm about to tell you didn't start with Lagrangians. They actually started with people building the equations of motion first, and then working backwards to what the Lagrangians should be. I'm giving you the Lagrangians, and then we'll get the equations of motion because when we talk about interactions, we're going to work at the level of the Lagrangian instead of the equation of motion. So the history of this is really complicated, and it's very backwards. But I'll try and point out, along the way when I can where things came from. But right now that minus sign seems completely unmotivated. Okay, but let me get to the equation of motion, and then it might make a little bit more sense. No, I'm not on that. I'm on these. Okay, so let's do it. What can we do with this?
A lot.
We plug it into the Euler-Lagrange equation of motion for fields, right? So I'm just going to say that because I'm going to put lots of things in for the field. Okay? So in this case, my field is really just phi. So this is the expression I wrote before, where in this parenthesis I'm putting phi everywhere. And let's just do this, because you need to see this once in detail. So you've got two terms to construct. One of them is easy and one of them is hard. I'm going to do one. If you do the other, I'm going to do this one. Okay, now you guys can do this one. Yeah.
Shouldn't there be an additional del in that, like I wrote there? To the left.
Yeah, that's that. Yeah.
Okay.
Thank you. I've never actually tried to write the Euler-Lagrange equation without putting a field in, so I wasn't comfortable with parentheses. But you're right. Yeah, that's what it should look like. Okay, no, I'm just kidding. I'll do this for you.
What?
All right. So we're just going to hang on to that derivative for a moment. What I need to do is I need to take the partial of the Lagrangian density with respect to the derivative of phi. Okay, now looking at it, it kind of feels like that thing is squared, right?
Yeah.
Kind of feels like it's squared. Okay, it turns out it is squared. But in order to work that out, it probably helps, and this is going to help you in your homework, so pay attention. It probably helps to write it like this. Okay. And then the way that you can interpret this derivative is in some ways as a metasum. That is, I take so these are summed over, so I could call them anything I want. So I could say take the derivative with a mu here and a mu here, or take the derivative with a nu here and a nu here. And both of those make sense because these two terms are both d lower mu phi and d lower nu phi. Okay? So if I do that, if I do it with the mu, then I just get this guy. So I'm left with 1/2 eta mu nu d nu phi. And then if I do it with the nu, I'm left with this guy. Everybody see that? Are those different? No, they're exactly the same thing because at the end of the day, all of these indices are summed. So there's no reason why I couldn't just call that nu and call that mu. And then they really do look identical. No, they looked identical before. Oh, yeah, no, I can switch these because it's the metric. My apologies, guys. Okay, so in a sense that this looks like something squared, it really is something squared. You just have to be a little bit careful because this is lower and this is upper. You're going to do a problem in your homework where you have to be really careful with this. And I'll show you the example in just a minute. Okay? But at the end of the day, we can put all this together and write down the corresponding equation of motion for a scalar field, right? We have this minus this has to equal 0. So we have minus mc over h bar squared phi minus this guy, which is just twice half of something, so if I go ahead and use the inverse metric to raise this index, then I can write this as d mu phi. So let me go back. These are the same terms, so I add them together and the halves go away. I keep this guy, and I use the inverse metric to raise this guy to become a nu, and then these two indices are the same. In fact, if you're really uncomfortable with it, I'll call that nu. It doesn't matter what I call it, it's repeated. Am I on board for that? You good? Sure? Okay, this is all equal to 0, so there's really no reason to hang on to those minus signs. And now we have a very famous equation. Does anybody know what this is called?
It's like the Klein-Gordon.
It is the Klein-Gordon equation. Okay? So this is the Klein-Gordon equation, which was, so this is an answer to your question. This was the first attempt to relativize Schrodinger's equation. So if you take Schrodinger's equation, it is definitely not relativistic. It's got a time derivative, okay? If you take Schrodinger's equation and you just do the minimum amount you think you need to do to get a relativistic version, you end up with this equation. Okay? And it ends up looking like what you would think, but in order to get this equation, your Lagrangian had to start off with a minus sign there. That's why I'm saying in the Lagrangian, the minus sign is totally non-intuitive. But in the way that this was derived from relativizing the Schrodinger equation, it makes a little more sense. And if you want to see this, you can look this up in a million resources. They're deriving the Klein-Gordon from the Schrodinger equation. Yeah?
So in this case, are we just ignoring the interaction term, or is this...
Yeah, I'm just focusing on the free term.
Okay, so that's not like a property of spin zero particles that we don't worry about the interaction term.
No, I'm going to ignore interactions for all of the cases. And then we're going to, in a couple of weeks, introduce the interactions. So I'm focusing on the free term for the scalar, and now I'm going to do the vector, and then I'm going to do the spinner. Okay? All right. So that this is... All right, well, remember this Lagrangian. We'll use it later. All right, next up is we're actually going to skip spin a half and go to spin 1. And then we'll come back to spin a half. So if we're doing spin 1, we're dealing with vectors. And what part of the standard model is this going to be relevant for? Yeah, the force carriers. All of the particles that mediate forces are vector particles, or spin 1 particles. So this is obviously an important thing that we're going to have to use at some point in the standard model. Okay, so you can think of these as the force mediators, what are often called the gauge bosons. And we're going to get into the details of that in due time. But for now, let's just remember they're an important part of the standard model. So what does the Lagrangian in this case look like? Well, it's a little bit more complicated. In this case, the free Lagrangian looks like the following. Minus 1 over 16 pi f mu nu plus 1 over 8 pi mc over h bar squared a mu. So that's pretty intuitive when you think about it, kind of. Not really, but not at all. Okay, so let me go through and point out some things in here that hopefully will make you feel a little bit better about what otherwise looks like a completely unmotivated Lagrangian. Okay, so here our field was phi. So you see where you've got sort of two derivatives of phi. You've got a quadratic derivative term. And then the mass is phi squared. Here, the vector particle is a mu, or the field is a mu. So our mass term looks about right. Yeah, there's some funny factors here, but it's basically a mass quantity times a squared, which is analogous to what we did with the scalar. Okay? Yeah?
Is
That is like the F mu nu and the A mu's, are those the...
I'm about to tell you what F mu nu is. I haven't told you what F mu nu is. So then you're like, wait a minute, what's that, Flournoy? Starts with F. Yeah. Okay, F is what you probably have seen F to be. So in many cases, but not all cases, F, let me do it down here, F mu nu is defined to be d mu A nu minus d nu A mu. And then if you need F upper mu nu, which you do to form this, you can just build it by applying two factors of the metric to the F with the lower indices. Now, the reason why we have this funny subtraction is not at all obvious, and it won't be obvious until we talk about interactions. It turns out that this combination is gauge invariant. If you just had one of them, it wouldn't be gauge invariant, and we'll see that when we talk about interactions. So again, there are aspects of this which I just can't motivate right now without a lot more detail. But at very least, I want you to look at this. F gets squared. Each F contains derivatives of A. So this thing is the square of the derivative of A, which is essentially the same thing as what we did in Klein-Gordon here. Okay? Everybody see that? So we're seeing the same sorts of ingredients arise in each of these free Lagrangians. Yeah, there are some coefficients that are a little bit different, and there's a little bit more complicated structure here, but hell, this is a vector and that's a scalar. You should expect things to be more complicated. It's also more complicated because this is a force particle and this is not. But we won't be able to understand that until we talk about gauge invariance and interactions. Robin?
So even though spin 1 is a vector, we still get a scalar out of the free Lagrangian?
Well, the Lagrangian has to be a scalar, remember? Okay. That's the bottom line. But now I'm going to show you what the equation of motion looks like from this.
Okay.
All right? So I'm not going to do this in detail because anybody want to guess why? Yeah, you're going to get to do it.
You said that last time.
So I want you to be aware that this time the field carries an index. So we've got to be really careful about where our indices are and what they're doing. All right? So if I'm going to vary the Lagrangian with respect to A lower mu, I could do a variation with respect to A upper mu or lower mu. Conventionally, we write the equation with lower mu. All right? But if I do the variation with respect to A lower mu, then that's the quantity I put there. But then this derivative has to have a different index. Because this derivative gets summed with, this index gets summed with that index. So I don't want to put these two to be the same. So overall, this term has one lower index. Wait, that, hold on, shit. Oh.
They're one upper.
Yeah, this guy's, hold on, this guy is, oh yeah, sorry, you guys are right, yeah, I just can't see it. Yeah, this is an upper index overall, and this is an upper index overall. I was like, oh. Okay, yeah, thank you. You're telling me the right answer, I'm just ignoring you. Okay, if you stick this Lagrangian in, and you take that and you find that equation of motion, you get something that looks like this. Okay? And you're going to do this in your homework. It's just doing the usual thing. You know, you can take the derivative with respect to A mu. That's pretty easy. You can do that in one step. The tricky part is taking the derivative with respect to the derivative of A nu. And that's where you got to peel these apart. Okay? So pay attention to the example I did with Klein-Gordon here, when I used the metric to expand that out. Okay, this is called the Proca equation. I'm not going to ask you if you know that, because none of you do. But if I take this equation and set n equals to 0, it gives you something that you should know. What is that?
Is that part of Maxwell's equation?
Yeah, it's half of Maxwell's equation. Okay. The fact that the Lagrangian and the equation of motion for a vector field only gives you half of Maxwell's equations is an often poorly understood aspect of electromagnetism that most physicists don't even appreciate. Okay? This will give you essentially the del cross B minus partial E partial T equals 0 and the del dot E equals 0 equations, where if you had an interaction, you would put in some current on the right side of that, and you would put in some charge density on the right side of that. But this is non-interacting. This is just a free electromagnetic field. So there's nothing that's sourcing it. Right? So it satisfies Maxwell's equations in a vacuum. The other half of Maxwell's equations actually correspond to a condition on the geometry underlying electromagnetism, which most physicists don't really properly understand because you actually have to formulate electrodynamics in terms of fiber bundles to understand where that geometric condition comes from. But just it's a moral lesson here that half of Maxwell's equations you get from dynamics. The other half of Maxwell's equations are not dynamical. They're a statement about the geometry. And it's in fact that other half that you have to modulate if you want to look at magnetic monopoles, for example. Magnetic monopoles are geometric configurations in electrodynamics. They're not dynamical. But we can talk way more than we have time for about that. Okay, so last guy. I saved him for last because he is definitely the worst, as you could probably have guessed.
Well, best for last.
Spin a half. These, of course, are those good old spinners. What are these relevant for in the standard model? Everything, pretty much. Every matter particle. Every fundamental matter particle that exists is a spinner. So this is the important one. Ready? Here we go. I, H bar C, psi dagger, or sorry, psi bar, gamma mu, d mu, psi, minus mc squared, psi bar psi. That should not be intuitive. It's only got one derivative of psi. Woo! M is not even squared. Woo! Okay? This does not look at all like this. And it don't look at all like that. Okay? Magically though, there is a connection between these things, which we'll talk about next time. Okay, but let me very quickly crank through what the equation of motion from this would be. And this is actually straightforward. It's actually much easier than this guy. Okay? First of all, and this is not intuitive, and we'll talk about it more next time, I can treat psi bar and psi as separate fields. So I can vary with respect to psi bar, or I can vary with respect to psi. You might go, wait, you build psi bar from psi. Okay? But for reasons we'll talk about next time, you can treat them as independent fields. So if I take the variation with respect to psi bar, so if I say partial L, actually let's do psi first, that's easier. Partial L partial psi minus d mu partial L partial d mu psi equals 0, we can do this instantly. Because you'll notice that this derivative just gives me this. No, sorry, I don't do this with bar. Sorry, yeah, bar is easier. What's this term? Say it. It's 0. There's no derivative of psi bar. So this whole term goes away. The only one you have to do is this, but literally you just peel off everything that multiplies psi bar. All right, so in this case I have I h bar c gamma mu d mu psi minus mc squared psi equals 0. Okay, now in most texts we take gamma mu d mu and we define it, and you can thank Feynman for this, to be d slash. Okay, and then this equation becomes d slash psi minus I d slash psi minus m c over h bar psi equals 0. Okay, that is the equation of motion for a spinner.
Wasn't that just a free spinner?
For a free spinner, right, for a free spinner. Where this d slash, remember, is gamma mu d mu. So I told you those gamma matrices were going to come in useful. Okay? This is what is famously called the Dirac equation. Okay? If you instead, and this is really interesting, if you instead did the variation with respect to psi, it would look very different because there is a derivative with respect to psi. But this term doesn't involve psi by itself. It involves psi bar, but it involves a derivative with psi. Of course, this term is a little symmetric. But it turns out if you do this with respect to psi instead of psi bar, you get this equation. It actually ends up looking almost identical. The fact that it looks almost identical is really weird because the way that you get it, you know, when we did this, we only had this term playing a role. This term was trivially 0. When you vary with respect to psi, both of these contribute.
Isn't that just the conjugate of the Dirac?
Exactly. This is actually the adjoint of the Dirac equation. Okay? Now, this looks completely non-intuitive. Why is there only one derivative instead of 2? Why does the mass do that? In order to give you some intuition, insight is more the appropriate word. This is never going to be intuitive. In order to give you some insight as to why this is the case, next time we meet, we're actually going to solve these equations. And in solving them, this is why the next few weeks is going to be fun, we're going to discover one of the most important properties of the Dirac equation, and that is that it predicts what? Antimatter. Okay? And that is going to be the source of this strange difference in the Dirac equation and the Dirac Lagrangian versus what we see for scalars and vectors. But more on that next week. Yes.
Does this minus dealing fields, does that include all spin particles or just
Okay, so this is not the photon, right? Because this would be 0.
Yeah, no, but
But no. The answer is no. The reason the answer is no is this. This guy is going to look This is going to look the same.
it looks the same, but just like
But this term is going to be different for different reasons for the
I didn't go hard yet.
okay.
That difference actually is very, very interesting because that's going to be the point where we see that unlike the photon, which doesn't interact with itself, and other vector bosons interact with itself. Exactly from the
Alright, sweet.
Move, Matt. Move.
Can you turn the camera?
Yeah.